All right. I don't know if you know this, but we are actually past the halfway point in the semester. Class 21. I think we've got 40 classes total, if I remember right. So we're past the halfway point. And the next class, class 22, we've got our exam. Exam 2 next Monday. We'll start at 9 o'clock instead of 9:05. Go until 10:45 if you need it. Don't forget your calculator and one note card. You can write it in front and back, 3 by 5. I always say this though, know the material well enough, know how to do the types of problems that I said are going to be on the test well enough that you can do it without a note card. That's the kind of practicing that you need to do well on the test. So we'll go ahead and look at the topics, excuse me, on the test down here. For exam 2 types of problems, though I'm not going to have time to go into depth on every single one here. I'll focus on certain ones for the most part. I think it would be good to start off talking about possible proofs, which is down here at the bottom. I'm calling it an unspecified proof of types we've discussed in class, including today's class, including types I'll talk about here in a few minutes. What other type did we have? I think it was Monday. We talked about proving the linearity principle, essentially. That if you've got two solutions, y1 and y2 of some linear system, that a general linear combination of those is also a solution. y1 and y2 are functions of time here. It's for a linear system. And the main fact that you needed, first of all, was that matrix multiplication is linear. And we proved that in the 2 by 2 case as well. That's another proof you should be able to do. We did that on Monday as well, I believe. I think it was Monday. This property, well, and in fact, you can generalize this to a linear combination as well. I probably should have just written that down. I think I did this as 2 separate properties, if I recall correctly, but you can write it as one single property. Should be able to prove that kind of thing, and you should be able to prove, again, like I said, that this is a solution of that. It's based on this property, but it's also based on the linearity of differentiation. The DDT operator, the fact that that applied to a linear combination gives you the same linear combination of the derivatives, k1 times y1 prime plus k2 times y2 prime. So the key thing is those are the ideas that are necessary to prove what you want to prove, that this is a solution, and then you actually need to write sentences. You need to show the details and explain why things work in an argument. Arguments should be written in sentences. What's another example of a type of proof that could come up on the test? Well, this is one I wanted to do on Wednesday, but we didn't have time. Let's first write the statement. Suppose Yre, excuse me, I'm saying the wrong thing. Suppose y is a complex valued function. Got the I in there, square root of -1. Yre is the real part of this complex valued function. It's a vector valued function. You can think of it as a 2-dimensional vector. Actually, it could be an n-dimensional vector. Ym is called the imaginary part. Both Yre and Ym have no imaginary numbers in them. They are real vectors. The imaginary part comes from the fact that this thing is next to the I there. Suppose this is a solution of a linear equation. I'm not going to specify what the matrix is. In our examples, A has real entries. Okay? So that's an implicit assumption here. Show that each of these functions individually also solve the differential equation. Yre and and Yim also solve the differential equation. That's what you want to prove. So let's write this out in sentences this time. You're making an assumption. You want to get somewhere. You want to show something. You got to know what you're doing, first of all. What are you assuming and where do you want to go with it? Then the question is, how do you get there? How do you get from the assumption to the ending thing that you want to show? Any ideas? Maybe I should start the first sentence at least. Since we're assuming this, you can say by assumption, dy dt equals a times y for all t. There's really a t there. I'm not writing it. Y is a function of t. I could put a t here. This is one situation where I'll let you be a little sloppy there. But you should understand y is a function of t here. So by assumption, for this particular function, maybe that's worth adding in here. For y equals Yre plus Ym, which I'm imagining, which I'm assuming is some particular function. We know this is true. For all t. Let me erase that t there, but I'll put for all t to remind myself that this does need to be true for all t, and that depends on t and that depends on t. A doesn't depend on t. A is a constant matrix. Maybe by writing that first sentence, maybe that gives you a little hint about what you think I should do next.
Matrix.
No? You're thinking too fancy. It's simpler than that. Ideas? Look at that equation too, by the way, in addition to this one. That's even more complicated than we need.
Take the derivative and then compare it to what we have on the left. I think that's what's behind you on the board. So we take the derivative of it and then possibly compare it to that.
Yeah, and by take the derivative of this, by definition, really, it's the derivative of that plus I times the derivative of that. Now you might wonder, is that a good definition or not? It is a good definition and is what we want here. I suppose you could say by linearity if it's not the original definition. It really is a definition, but you could call it a linearity definition. I'll just say by linearity of the derivative operator. We have to define what it means to take a derivative of a function that looks like this, and we haven't technically done that. So I'm sort of calling it a property, but it really is a definition in this sense. By linearity of the derivative operator, dy dt is, I'll use primes here, Yre prime plus Im prime. Just to save a little time, I could use the ddt notation there too. Our assumption implies then that, well, dy dt equals a times y. In other words, this thing equals a times y. Yre prime plus Im prime equals a times y. But what is a times y? It's a times Yre plus Iyim, because that's what y is. What does it mean to multiply a matrix times a combination of vectors with an I in there? Well, that really requires a definition as well, but I'll go ahead and call it linearity of matrix multiplication. Using linearity of matrix multiplication, this means that this thing equals that when the A is distributed through. Yre prime plus Ym prime equals Ayre plus A times Iym, and the I is a constant that can be factored out. I'm using a linearity property there too, which I think, again, in a sense, it's really more of a definition in this context. But that's what we mean by that kind of multiplication. I suppose you could think of it as a property if you first define what it means to add these vectors by adding their components in the normal way that you would add a real plus I times another real. Then you could think of it as a property more. If I make a definition of these derivatives and this multiplication more component-wise, then you could think of these things as being properties that you could prove. And right now we're just trusting that you can do them, and you can on the test too. You can trust that these properties hold. Is that it? Are we done? What do you think? Can I say QED right now? Quadratic Demonstrandum, I think is how you pronounce it. Latin for we're done. We did what we wanted to do. Are we done? Is there anything else to say? Think about your goal. Did we show that? I want to show that both of these functions solve the differential equation. Have I done that by writing that equation there? Oops, I made a mistake, didn't I? I forgot my I. The answer is yes. We are basically done. However, it should be mentioned that the only way for two complex quantities to be equal is if their real parts are equal and their imaginary parts are equal. That should be mentioned. We can write that as the sentence coming up here. Since the only way two complex quantities, whether they be numbers or vectors, in this case they're vectors, can be equal, again under the assumption that the things that are, the thing there and the thing next to the I are actually real. No imaginary numbers inside them, is for the real parts to be equal and the imaginary parts to be equal. That's worth saying, even though it takes 30 seconds to write out, it's worth it. Therefore, do 3 dots for therefore, Yre prime equals Ayre, and Ym prime equals Aym for all t, and I'm out of room. You could say QED at this point. Might also be nice to add, this means Yre and Ym solve the differential equation. That might be a nice touch to add, but I would be okay with you just putting QED at this point. Well, PTO for praise the Lord, right? There's the Christian view on ending proofs.
He knows a Christian mathematician. He can do that.
All right. So something like this could be possible. How could I modify it? Maybe I do go back to a scalar situation instead of a matrix situation. What else is a possibility? I don't want to do a full proof because that took, what, 8, 9, 10 minutes? What other kinds of facts should you be able to prove? Well, there's the one on the exam from last year. I didn't ask them for a proof, or full proof. I just said to write down some equations and give brief reasons for each equal sign, so they didn't have to write sentences, and I'm going to want you to write sentences. Their pseudo-proof, sketch of a proof, was to show that this function solves the differential equation when you assume what? What do you think? What would we need to assume about that function? Take a guess based on the notation. Assume lambda is an eigenvalue for A, and V, don't just say is an eigenvector for A, say an eigenvector for A corresponding to the eigenvalue lambda. Eigenvectors always go with eigenvalues. Different eigenvalues have different eigenvectors. There's always the correspondence. Though for any given eigenvalue, you take an eigenvector, you can multiply that eigenvector by a non-zero constant and get another eigenvector for that same eigenvalue. So you need to assume lambda and V are eigenvalue eigenvector pairs, eigenstuff, if you will, corresponding eigenstuff. Okay, well, it's a matter of plugging the left-hand side and the right-hand side and using properties and simplifying and using the fact that you're assuming lambda and V are an eigenvalue eigenvector pair for A. You are really assuming that we know how to differentiate a function like this as well. V doesn't depend on T. There's your dependence on T. This is not a matrix exponential here. Lambda and T are scalars. That's a regular exponential function. You can differentiate it by differentiating the scalar in front, in this case with the chain rule, and leaving the constant vector over there on the right. That's the left-hand side. What's the right-hand side? I've got to multiply A times e to the lambda t times V. How do I do that? Again, I'm doing this abstractly. We don't know what A is, we don't know what lambda is, we don't know what V is. We have to think about abstract properties. What's an abstract property here do you think that I should use?
Just a constant.
That's a constant. It can be factored out. That's a linearity property of matrix multiplication, one I've already mentioned. Why is that a good idea? What did we gain out of that?
You got a matrix times a vector.
Matrix times a vector, and what's special about that vector?
It's the eigenvector.
It's an eigenvector for A corresponding to the eigenvalue lambda. So, what does AV equal? Lambda V. By the way, AV does equal lambda V, but you're doing two different operations here. That's a matrix times a vector. That's a scalar times a vector. This does not imply A equals lambda. A is a matrix, lambda is a number. These two things are both vectors. A times V and lambda times V are both vectors. It's an equality between vectors. You can't cancel the V's, though, to say A equals lambda. That doesn't make any sense. Am I done? Compare Well, essentially, but you really should use an algebra property. It's really the associative law, along with, if you want to write it like that, a commutative law for multiplication. I can write it as lambda e to the lambda v, lambda t times v. And they're equal for all t. That's really the key step right there, using the assumption that lambda is an eigenvalue of A and V is a corresponding eigenvector. That's the key step that makes this work. Okay, so that's the idea. You work at putting that kind of thing in a sentence structure as another possible proof. By the way, with this kind of proof that we did on Monday, I didn't have to stop at two solutions. I could have said I've got 3 solutions, y1, y2, y3. Is a general linear combination of those 3 solutions a solution? And the answer is yes, even if the matrix is 2 by 2. And you should be able to show that. That doesn't mean that I can write the general solution like this. This is not the way you'd want to write the general solution, at least it's not the most ideal way. The more ideal way is like this. You only need 2 linearly independent ones. I'm assuming in saying this is the general solution that y1 and y2 are linearly independent. With the proof that I talked about, though, you don't need to assume that. You don't need to assume this. In fact, 3 vectors in R2 in 2-dimensional space can't be linearly independent. So in saying this is a solution, I'm not saying anything about linear independence.
And since, if you said that y1 and y2 are linearly independent, then y3 is just a multiple or a linear combination?
It would be a linear combination of y1 and y2, yes. But again, you should be able to prove that if I assume these 3 things are solutions of that, then this general linear combination is also a solution. The proof is essentially the same, just got this extra term to deal with. Okay? Again, I'm not saying anything about linear independence when I talk about that. All right, yeah, that took a while. But that was pretty good, I think. Another one I want to talk about is this one. So for today's assignment, you have particular examples with matrices that have complex eigenvalues and corresponding complex eigenvectors, and then you end up using Euler's formula to find the general solution. The test involving complex numbers, the question involving complex numbers on the test, the matrix is not going to be a purely numerical matrix. Its entries are going to involve letters, constants, maybe A and B. And I'm going to want you to find the eigenvalues and eigenvectors in general solution in that situation, which sounds like it could be really tough. But it actually, in some ways, is easier because the matrix I'm going to give you is going to be pretty special. And the answers are going to turn out fairly simple in the end. Let me consider an analogous problem. Consider the matrix capital A equals, let's make it fairly simple, A, B, B, A. Where A and B are any real numbers. Of course, I'm thinking about the differential equation as well. I'm after the general solution of this. So I need to think about finding eigenvalues and corresponding eigenvectors. Non-numerical entries, they represent numbers, but they're not specified. Constants. So it seems like it could be harder, but that's a pretty special kind of matrix there. So maybe it's not too bad. The determinant of A minus lambda I. By the way, you should also know the geometric motivation for eigenvalues and eigenvectors. I suppose I could test you on that as a proof type of problem. I haven't written the proof actually yet, if you're wondering. I haven't figured out which proof I want to put on here yet. So I'm still thinking about it. You should review the geometric meaning of eigenvalues and eigenvectors, the motivation for that in terms of straight line solutions. Maybe I could put that kind of thing into some proof somehow. Anyway, coming back here, we've got to take the determinant of this matrix. By the way, in case I'm alive in 20 years and still teaching, this is 2035, it's 2015 right now. In case I'm alive still teaching in the future, these are not necessarily your problems if you're watching this in the future. I was going to say that, I forgot to earlier. It's kind of fun. By the way, this is the 30-year anniversary of Back to the Future. We don't have hoverboards. Right when he went into the future, he went to 2015. And they had hoverboards. We don't have hoverboards. I think in October is the anniversary, so that's something to get excited about. Not quite as much fun as Pi Day, perhaps. Well, maybe it's more fun. That's something that's coming up. Thinking about the future is what got me thinking about that. Okay, so the determinant, a minus lambda times a minus lambda is a minus lambda squared minus b squared. That's your characteristic polynomial. If you write it in standard form, you'll get positive lambda squared minus 2a lambda plus a squared minus b squared. What are the eigenvalues going to be? Set that equal to 0. Solve for lambda, use the quadratic formula. You shouldn't need to put the quadratic formula on your note card. Shouldn't need to. Don't say in class, though. Don't hum to yourself. Do it in your head. Of course, you can put it on your note card if you want. You should know the quadratic formula for this class. Negative b is 2a, because of the negative sign there. Then I got to square that. The negative sign doesn't matter. I get 4a squared minus 4ac, meaning minus 4 times 1 times that. That's the c there. Over 2a is over 2 times 1. The a in the quadratic formula is not this a, it's 1. And look at this, this simplifies pretty nicely. The 4a squares will cancel. You'll just be left with the square root of b squared. So you can actually write the eigenvalues as 2a plus or minus, I forgot the 4, 2 square root of b squared over 2. The 2's will cancel. You're going to get, well, technically speaking, square root of b squared is the absolute value of b in general, not b. However, because of the plus or minus, it won't matter if we just write a b. The 2's cancel. The eigenvalues are a plus or minus b. No i's in there. Those are real. So what have we found? We found that matrices like this cannot have complex eigenvalues. You get 2 real eigenvalues. They'll both be positive, meaning this will give you a source if and only if a and b are both positive and a is greater than b, so that a minus b is greater than 0. Yeah. If they're both positive, well, I guess I should say, sorry about that. Well, let's see here. A plus b is positive if and only if a is greater than negative b. A minus b is positive if and only if a is greater than b. B could be positive or negative. Looks like as long as a is greater than the absolute value of b, those will both be positive. Is that right? As long as that's true, which means a itself has to be positive if I'm thinking about it that way. yeah, there's no way if A was negative that they could both be positive. They could both be negative if A is less than the absolute value of B, and if A is negative. Maybe it's the, let's see, I should be careful. Maybe I shouldn't go ahead and get into this. They can both be negative if both of those are true. Which means A has got to be negative, so actually I've got to write this as A is less than negative absolute value of B. Okay, you're not going to be tested on that kind of thing. The main thing I want you to see is that these eigenvalues are actually pretty easy to calculate. What about corresponding eigenvectors? Let's just do one of them. How about the corresponding eigenvector for A plus B? Assuming I've done everything right, I can just focus on one of the rows, remember? Thinking of it as a row more of this one. Replace lambda with the eigenvalue. That's the coefficient of x there, and the coefficient of y is going to be b. This simplifies to negative b. Then the b's can cancel. Eigenvectors satisfy the condition that y equals x. In other words, they are multiples of this one, and you can use that one as a eigenvector. This was a minus b in there. Then I guess this would be a plus b, and this would be y equals negative x. I get 1, negative 1, or negative 1, 1. Okay, that's the kind of thing I'm talking about here, except in the complex eigenvalue case. By the way, the general solution here would be k1 e to the a plus b times t times the vector 1, 1 plus k2 e to the a minus b times t times the vector 1, negative 1, or negative 1, 1, or any non-zero multiple of those. There's infinitely many ways of writing the general solution. Only one answer for initial value problems. When you simplify, you should get the same answer for initial value problems, no matter how you write the general solution, as long as the general solution is correct. Can I clarify anything here? All right, third thing to go over today is more with the matrix exponential and flows. These are going to be our three main things today, I think, in reviewing. The other things I think I feel more comfortable with you reviewing on your own. I actually am going to post a notebook on Moodle that explains the matrix exponential more fully and its relationship to flows of linear systems. Let's go ahead and consider an example in that one. In this notebook here, it's just extra reading. It's there's no questions inside of it. Let's consider this example right here. That matrix. Actually, maybe we will do a quick calculation of the eigenvalues. This one may end up being complex, just as another example of a complex number calculation. By the way, if I put absolute value signs around the matrix, that actually means take the determinant of the matrix as a shorthand notation. Doesn't mean the determinant is positive, it could be negative, but that's a shorthand notation for the determinant. So in this case, I get negative 1 minus lambda squared minus 2 times negative 2 will be plus 4. Lambda squared plus 2 lambda plus 1 plus 4 is this. Your eigenvalues are going to be negative 2 plus or minus square root of 4 minus 20 over 2. square root of a negative number there. You're going to get the square root of negative 16. That'll be negative 4i. The 4 will cancel with the 2 to give you 2. Looks like negative 1 plus or minus 2i are the eigenvalues. Let's check that here. And let's also see the corresponding eigenvectors. Eigensystem. Yep, I did the eigenvalue calculations right. Corresponding eigenvectors are complex as well. Remember, when you do this calculation, as far as finding the general solution with Euler's formula, you only need to consider one of the eigenvalues. That's the only bit of good news with this complex number stuff, I think. You only have to consider one of the eigenvalues in the corresponding eigenvector, which does remind me, by the way, that with that equal lambda t times v, actually, I didn't use any assumptions about the nature of lambda or v. They could have been real numbers and real vectors, or complex numbers and complex vectors. And that calculation that I erased here would still work. The straight line solution stuff doesn't work because there are no straight line solutions when you have complex eigenvalues. You have spiraling solutions. So you can't really interpret this geometrically, these eigenvectors. You can't really interpret those geometrically. You have to interpret them algebraically. Anyway, that's what it ends up being. The real part is negative for both of these. In fact, these complex eigenvalues are what are called complex conjugates of each other. Complex conjugate was that thing that I mentioned the other day that's a trick you can use to divide complex numbers. In fact, whenever your matrix is real, when you've got complex eigenvalues, they have to be complex conjugates of each other. Negative 1 plus or minus 2i. Okay, that's what happens here. The fact that the real part is negative means you're going to have a spiral sink. If the real part had been positive, you would have a spiral source at the origin. The origin still is the only equilibrium point because the determinant of that matrix is non-zero. What if the real part's 0? Then you have something called the center. Solutions either look like circles or ellipses, which is what happens when the real part of the eigenvalues is 0, but the imaginary part is non-zero. By the way, we haven't dealt with cases where 0 is an eigenvalue yet. That's section 3.5 after the test. Okay. Anyway, so notice down here, though, now that I'm using the matrix exponential, really to define the flow. How do we write this by hand, and how do we think about it by hand? This is not completely standard. This is just the way I'm having you do it. It's fairly standard. First of all, when I write the matrix exponential by hand, and I think of this as a solution, I write it as e to the t times a. Some people write it as e to the a times t, which is fine. Either one's fine. I like putting the scalar in front of the matrix to emphasize that it's sort of easier to emphasize that t is a scalar times the matrix. You're multiplying every entry in the matrix by t. If you write it that way, there could be confusion. People might think t is a vector. Actually, you can pre-multiply matrices by vectors as well, but this is perhaps a little less confusing. If I multiply this matrix times that vector, that's the unique solution, in fact, of the initial value problem, d1t equals ay, y of 0 equals y sub 0. Okay, that's what I call the beautiful generalization. Okay, that's my name. It's a beautiful generalization of the scalar case. That differential equation, this initial condition, has unique solution y0 e to the at, where a is a number now, and y is a number as well. Y is a vector here, a is a matrix. A similar kind of thing still works. Except you put the initial condition to the right because it's a column vector. You've got to multiply the matrix, 2 by 2 matrix times that 2 by 1 column vector, at least the way we're thinking about it. They match. That's why it's beautiful. That's why it's a generalization. It's beautiful that that works. That the matrix exponential defined in terms of a Taylor series, that this still works. It doesn't mean it's easy to calculate, but it works. we're letting the computer calculate it for us for the most part. Though I do give you in this notebook here some intuition in the simplest kind of case, up here at the top, where your matrix is diagonal, and I'm making the diagonal entries negative to make a sink in this particular example. Here's the general solution, which you can get just by guessing. You don't even have to think about eigenvalues and eigenvectors. You could, but you can get it by guessing. That's actually what I talk about here, is a completely decoupled system. And remember that in the diagonal case, the matrix exponential of that kind of situation would be this thing. And if you multiply that matrix times this initial condition vector, you do get the exact same thing that you get by guessing. So we can understand why it works in the case where the matrix is diagonal. That's the simplest kind of case. It's a completely decoupled system. Okay, so I talk about that there. What about flows? Well, sometimes, as usual, I call this not just y of t like the book, but phi of t, and put a subscript to specify the initial condition. When I use that phi, I put a subscript, and that subscript represents the initial condition. T is the variable for this function. You graph this function, it's a parametric curve. You graph it in the phase plane. You're graphing the solution curve. This is what you're used to. The flow is just a change in perspective. Some people, by the way, don't change to the fancy phi. I just like it. It's so pretty. I like changing to the fancy phi, but to also emphasize the conceptual distinction. It's related to the other phi, but it's not the same thing. It's got the same formula, essentially. I put the t in the superscript there. I put the y there, and I'm not calling it y0 anymore, because ultimately, when I think about this function, I want to think of t as constant. And for different t's, I get different functions here. This is really a function of y. You could write this. It's the other phi sub y of t. It's got the exact same formula, except use a y without a y0. And think about it differently. Think of t as fixed. Think of y as the variable. For any fixed t, this defines a linear function of y. Actually, a constant matrix, t is fixed, times this variable vector. This is a linear transformation for people who are in linear algebra. Okay? We can do some neat visualizations with this, of the type that I showed you a little bit the other day. Down here I got some neat ones. Here's our example. I don't want to get into the details of the Mathematica here. You can think about them if you like. I will highlight the fact that I'm using parametric plot with two parameters that I'm calling u and v here, instead of one parameter, which is the usual way we use parametric plot. And here's the picture. So there we see a spiral sink. The origin is the spiral sink. Don't forget to put dots for your equilibrium points. You'll get a point taken off on the exam if you forget a dot. If I happen to ask you to draw one. And here we have a green region, a green blob that we could, for example, pretend is an oil spill or something less serious. I don't know. What else? Oil in general, or maybe milk. It's a blob of milk, green milk. It's going to move with the flow. Here I'm using flow in a more intuitive sense, a more fluid dynamic sense. Imagine this as being a thin sheet of fluid. What's going to happen as it moves with the flow? As I do let t change, I see images of this mapping under different values of t, images of this set, and it does what you think it should. It spirals around the origin. And in this case, since all the points go to the origin, it's got to get smaller. So the oil spill is disappearing. Maybe that's positive, right? The oil spill is disappearing under this flow, under this sink, this spiral sink. It actually continues spiraling around the origin forever and ever, getting smaller and smaller. Okay. In reality, it never reaches the origin. I hope that's always been clear. The origin's an equilibrium point. No other solution can actually touch the origin. They just approach it as t goes to infinity, in this case. So what should you know? I mean, this, you're not going to have to draw something like that. You should know the beautiful generalization that I erased here. You should know that that's how you define the flow. And you should know that you can pick a particular value of t, like t equals 1, and get the time 1 map, for instance, which in this case would be just e to the a times y. And you should also know that iteration of that function, just like in exam 1, iteration of that function with a recursive equation corresponds in a situation where your differential equation is autonomous, corresponds to following solution curves in the phase plane for a given initial condition by 1 unit of time as you go, if indeed I use t equals 1 here, which is the most common thing to do. So I'm creating this recursive equation. I got a certain initial condition, y0, that for the test, if I remember correctly, I think I picked something particular here. I think so. I mean, I tell you what the matrix exponential is too. I give you that on the test. I'm forgetting if I put something specific here or not. So I'm just talking about the idea here at the moment. You should understand that what happens is these yNs that are generated with this recursive equation and this initial condition give you the same points, in this case, as following the solution curve for that given initial condition n units of time. So here, that's t here. Plugging in n equals t right there. Meaning in this case, because of this formula, that that's the same thing as e to the n times a power times y0. Okay? Iteration of the time 1 map gives you this relationship. Iterating that thing follows solution curves at moments in time. It's like you got a strobe light, and it's mostly dark, but every second it quickly flashes, and you see where the solution curve is. As the seconds go by, you see a point moving. That's how you want to think about it. Why is this worthwhile? A couple reasons. Iteration is, technically speaking, a simpler concept than finding solutions of differential equations. It's a discrete concept, iterating this function. So that's one benefit of it. Another benefit is in chapter 5 at the end, we're going to see this kind of idea applied to a situation where you really have to apply it. There's really nothing else much you can do. Well, it's easiest to apply it in that kind of situation, I should say. We'll see a situation like that at the end of chapter 5. And we've got these neat animations. So that's something I would suggest reading to understand it better as you prep for the test. We're about out of time. You should, I don't know that I explicitly test you on this offhand, I don't remember, but you should know the facts that are in the second section up here at the top from Wednesday's topics. I didn't go over these topics on Wednesday, but they're here. Let's see. What facts am I talking about? Okay, it's these facts here. I'm stating these in terms of inequalities, but you could really focus more on the words. In the case of distinct real eigenvalues, when they have opposite signs, the equilibrium point at the origin is going to be a saddle point. That's something you should know. If they're distinct real eigenvalues and they're both positive, then the equilibrium point at the origin is going to be a non-spiral source. If they're distinct real and negative, it's going to be a sink. In the case of complex eigenvalues, in the complex eigenvalue case, it's the real part, the alpha is the real part here. Oh, where did I put that? Right here. I'm writing my complex eigenvalues like that, alpha plus or minus beta I. The alpha, the real part, determines whether it's a sink or source. It's a sink if alpha is less than 0, it's a source if alpha is greater than 0, it's a center if alpha equals 0. What about the beta? Well, how does that affect things? Well, technically speaking, if alpha is non-zero, the solutions are not technically periodic. They are sort of periodic. They oscillate with either a smaller and smaller amplitude or a larger and larger amplitude as you go. The beta, the imaginary part, affects the frequency of that. 2 pi over beta is the period, how much time between the peaks. And its reciprocal, beta over 2 pi, is the frequency. If you use standard units, time in seconds, that would be an amount in hertz, cycles per second essentially. If it's a large number, that's a fast frequency. It's oscillating very rapidly, and the period's small in that case. So beta affects that, if you wanted to know. I don't remember offhand if I asked something related to that because I wrote the test last week, but that, it is worth knowing, okay, and it is in the book. Any last minute questions at all? Don't forget that we start at 9. We'll see you then.